Hello and welcome back to Mr. Powers Teaches Math, algebra, anyway, binomial theorem stuff. We're doing a binomial theorem, and I would like for us to really understand the binomial theorem and make some connections with binomial expansions. That is stuff like this, binomial expansions, like x plus y to the fifth, equals x to the fifth plus 5, x to the fourth, y plus ... What does that actually get you when you multiply it out? There's a binomial expansion. So we want to make a connection to those binomial expansions, the combination notation, getting combinations, and Pascal's triangle. And you may not be familiar with Pascal's triangle, but that is this fun triangle here. And if you pay attention, you'll be able to see a pattern in this triangle. And so there's a lot of neat little connections with those three things. And hopefully we'll be able to get all that together here in the next 2 or 3 videos. So for now, I want to look at these binomial expansions and see what we can do with them. Okay. So binomial expansion. So first things first, let's do a nice easy one. If we're doing a nice easy one, we get x plus y squared. That's a nice, really easy binomial, and we're going to square it. So what does that mean? That means x plus y times x plus y. And we're going to get, well, how do we do it again? Just a reminder, we use the distributive property, but we use it twice. And I won't review that, but what ends up happening, hopefully you've realized this by now, what ends up happening is every term in each grouping, each parenthesis here, every term multiplies every other term in every other group. So the x multiplies the x and the y here, and this y multiplies the x and the y in there. Everything multiplies everything else. Okay? All right. So we get x times x is x squared. X times y is xy. Y times x is another xy. I could leave it xy or yx, I don't know. But we would combine these, right? And then y plus y is, or y times y is y squared. And then we usually like to write it like this. X squared plus 2xy plus y squared. Okay? And I did write this out here. Now you see, if you looked at the coefficients, it's 1 x squared, 2 xy's, 1 y squared. There's like the 1, 2, 1 there. Like, oh, this maybe, I don't know. I might be reaching there. We'll see. Okay. But why is that? So I want to look at that. Remember what I said, everything here multiplies by everything else. So it's almost like probabilities, not like probabilities, like the counting principle. Like I have 2 options. I get an x and a y from the first one. There's 2 there. I get an x and y from the second one. There's 2 there. How many ways are there to multiply everything out? There are 4, and we ended up with 1, 2, 3, 4 terms. And so there is this connection here with the counting principle. How many ways are there to get an x and a y? Right? How many ways are there to get an x and y? And we could do this with a tree diagram. Here, because there were 2 ways to get an x and y. I could get an x from the first one, a y from the second. That's here. Or I could get a y from the first and an x from the second. That's here. So there were 2 ways to get 1 x and 1 y, right? That's interesting. And we get a 2xy there. There's only one way to get 2 x's. X times x. There's only one way to get 2 y's, y and y. And we can see that really easily with a tree diagram. My first choice is x and a y. And then my second choice is going to be an x or y again. X or y again. And each of these results in a different outcome. Here we get x squared. Here we get xy. Here I'd get another xy or yx. And then here I'd get a y squared. And so we can see that counting there. We get all the options, same as when we multiplied it out. And there we go. So I'm going to do one more like this, but let's do it with x plus y cubed. And I'm just doing this. I'm being really thorough, maybe more thorough than I need to be, so we can see this relationship between the counting principle, like, hey, how many ways are there to do this? How many ways are there to do that? And this expanding binomials, because there is this neat little relationship, and it's hard to see sometimes. And if we can really see that it's going on, we're going to be in better shape. So x plus y cubed is x plus y times x plus y times x plus y. And again, it's going to be everything in the first term times everything in the second times, product, everything in the first factor. So it's going to be the x times everything in here times everything in here, the y times everything in here times everything in here. It's everything times everything else. That's how it ends up happening when we do the distribution, using the distributive property. We multiply this out. And so we already know the start of it, right? We could multiply the first two out, and we get x squared plus xy plus xy plus y squared. And then we'd have our x plus y. And I'm leaving those xy's as their own terms, because we already saw that. You know, you have two choices for the first decision, two for the second. We got four outcomes, four possible outcomes, right? But two of them are really the same. There's two ways to get one x and one y. Multiplying those first two binomials out. But now I got to multiply the second one out. So how would we do that? We would distribute again. Now, I'm going to distribute before combining like terms, just so we can see all those options happening. So first, it's the x times everything. X times all of this. Right? So, and then the y times everything. Let's see if I can fit it all in here. So we'd have x cubed plus x squared y plus another x squared y plus xy cubed. Oh, xy squared, sorry. What happened? Okay. There we go. All right. xy squared. Okay. There. So x times e for every term in here. And then we got to do the y times everything. So let's do the purple here. And we'll do y times each of these. We're starting at the left, though. So y times x squared first would be y x squared plus y times the xy would be xy squared. Oh, you know what? I do prefer to put my x's first. Sorry. So let's go ahead and write it. X squared y for that first term, and then xy squared, and then xy squared again. Okay. And then our last one, y times y cubed. Y times y squared, I'm sorry, is y cubed. Okay. Beautiful. And then, what did we end up with? 1, 2, 3, 4, 5, 6, 7, 8 different, if we thought about counting wise, there were 8 different outcomes. And if you think about this in probability, right, you have 2 options for the first choice, 2 for the second, 2 for the third. It'd be 2 times 2 times 2. You would get 8 possible outcomes. But of course, for us, we are multiplying everything in the first choice times everything in the second times everything in the third. We're multiplying these all out. So we're getting every possible outcome when we're doing this multiplying through with these binomials. How many ways are there to get an x every time? Well, it's only one way to get x and x and x. It's right there, right? How many ways are there to get one y in a term? We could go y times x, that'd be an x squared y, or we could go y times x times this x, or we could go this y times x times x. There'd be 3 of them. So we should have 3 terms with 1 y and 2 x's. So let's see, 1 y and 2 x's. Here's one, and here's one. There it is. X squared y, x squared y, x squared y. There are 3 of those. X cubed plus 3x squared y. And then if we kept going, of course, we'd end up with something similar. So that's enough of that. So plus 3xy squared plus 1y cubed. And that's a 1, 3, 3, 1. And what do you know? Back up here when I made this quick Pascal's triangle, 1, 3, 3, 1. Okay. One more time, though, to really show it why it is, again, why we're getting all of these terms. These are the result of picking an x and a y 3 times, because we did it to the third. And we can diagram that out once again with a tree diagram, x and y. Okay, so first choice, I pick one, and then I get another x or a y. I'll get x or a y, okay? And then the third choice, I'd pick an x and a y again for each one of these. And I would know all my possible outcomes, x times x times x, x cubed, x times y, x squared y, x times y times x squared y, x times y would be an xy squared. And then over here, x times y times x, that's an x squared y times y, that is x y squared, y times x, that's an x y squared, and then y times y was our y cubed. And so you can see we get the same exact result. This was every term. This is every possibility, every outcome. If you think of it as picking an x or a y 3 times. Okay, so that is all I wanted to do in this video. That takes us to 13 minutes, 14 minutes. It's just so we could see this connection, okay? So the next thing we're going to do is use that thinking to develop a formula for these so we can do stuff to the 5th, to the 6th, to the 8th really easily, okay? Using counting principles. It's a combinations. How many ways are there to pick 2 x's and a y? There were 3. How many ways are there to get 1 x and 2 y's? There are 3 ways. How many ways were there to get all y's? There's only one way, right? And so it is that combination thinking. We're finding combinations here. And so in our next video, we're going to write the formula out and go from there. And then we'll prove it. We'll prove that it works. So, well, we kind of did prove it already. But for now, that'll be enough. So until next time, enjoy doing math.